Okay, so vectors. What is it? If I Google it, the first thing somebody tells me is that vectors are objects with both magnitude and direction, right? Magnitude and direction. People have been saying this to me for years. I don't like it. I think it's not a good way to introduce them. So what I'm going to do is I'm going to tell you exactly what vectors are, and then we can kind of throw in that intuition on top in a minute. So okay, so that said, you heard my first beef with the pedagogy on vectors. Let's hop into it. Okay, so explicitly, what a vector is, here's like exactly what it is, or as close to exactly as we'll talk about it. A vector is just an ordered collection of numbers. So if I have a vector, first of all, the way that I write a vector is I just give it a letter, and then I put a hat on it. And the hat is kind of arrow shaped. That'll be significant in a second, I hope. So vector, hat. A vector is just a collection, an ordered collection of numbers. So for example, 1, 2, 7. That's a vector. 1, 18 pi. It's another vector. I could have 1, 18 pi, 47, 38.2. It's another vector. The number of different parts, the number of different numbers within the vector, is called the dimension of the vector. So this is a 1, 2, 3, 4, 5-dimensional vector. In physics, we're only going to really talk about up to 3, typically. So 1, 2, 3. Yeah, there we go. 1, 2, 3. Oops, I forgot my comma here. Sorry about that. So I separate each of these elements of the vector by a comma. So we'll talk about exactly what these elements are in just a second. Another way that I can write this vector is with letters. So I could say at the first index, at the first point of my vector, this first spot, here's v1, v2, v3. These are the 3 components of this 3-dimensional vector. So I'm using the word component now to describe each of these spots. 1, 2, 3. v1, v2, v3. Okay, so that's exactly what a vector is. It's just an ordered collection of numbers. In physics, we kind of throw a little bit more intuition on top of that by saying, like, usually these are spatial coordinates. So by convention, if I've got a vector, and it's a vector that's talking about space, the first index, the first spot, the first component is x. So this is the component of v in the x direction. The second index is always y, and the third index is always z. Today, we'll only talk up to 2 dimensions, so we're only going to talk x and y. Cool. All right, so that's explicitly what a vector is. Again, just an ordered collection of numbers. So an intuitive picture for what a vector is, and this is what I think usually people mean when they say magnitude and direction, an intuitive picture of what a vector is it's kind of an arrow. So usually people draw vectors as arrows, and a true vector always starts at the origin and points to some position in space. So if I'm dealing with x and y coordinates, let's say I had a vector k. I'm not going to use k. K is going to get confusing. Say I had a vector b, and this vector b points in x, y space, and its values are 2, 7. Okay, so if I wanted to represent vector b here, what I could do, once I've got an axis set up, give me just 1 second. What I can do is I can look at each of the components and then figure out how far over I need to go from the origin to draw in an arrow. So the first component, 2, tells me that I go over 2 on the x-axis. My second component, 7, tells me to go up 7 on the y-axis. So my vector is a line, a pointed line that starts at 0, 0 and goes to the point 2, 7. There we go. All true vectors start at the origin. So it's kind of a minor point, but vectors make perfect sense at the origin. We're going to get a little cavalier and start just placing them other places too. But a true vector always lives at the origin. Okay. One way that I might use a vector is to talk about something that has both magnitude and direction. So, for example, wind. If someone told me that there's an 80-mile-an-hour wind that's pointing northeast, The way I might represent that on a map would be to say, all right, I've got this vector. I'm going to call it v. This time v is for velocity. And v, I'm going to say is, what did I say, 80? I'm not going to give the components for it. But it's a vector v. And I said it's going 80 miles an hour in the northeast direction. So I might represent the speed of the wind by this vector v. It's pointing roughly northeast. And since it's an 80 mile an hour wind, the length of this is going to be 80 miles per hour. If I had a weaker wind, like a 20 mile an hour wind, pointing in the northeast direction, it would be a quarter the length. A quarter the length. Because, 20 is a quarter 80. Hey, Adam from editing here. I realized I made a little verbal typo there, so I wanted to clean it up. Anytime I talk about the thing that describes the magnitude and direction of motion, so the thing that describes like how quickly I'm going in a direction, I call that thing velocity. So this vector is always called velocity. The speed is always the magnitude of velocity. So here, this vector has speed of 80 miles an hour. The velocity is given by this vector. It includes the direction. I wanted to mention also that, as I said in the intro, vectors are like really globally useful. Like lots of folks use them for all kinds of different things. So whether it's like patient records or stock analysis, a lot of folks end up interacting with vectors in one way or another. Okay. I want to pull us over. This is getting a little esoteric, so let's pull us over somewhere else. Let's talk a little bit about vector vocab. So I'm going to use a couple of words throughout this. I want to make sure that the words make sense. So here goes. The first notion is of scalar versus vector. So a scalar is just a number, basically, a single number. So a scalar is just a single number. Single number. I can actually think of a vector in one dimension. Say it's 3, whatever. A vector in one dimension basically is a scalar. Pretty close. A vector is this thing that has both magnitude and direction. That's multiple numbers ordered. So we've just talked about what a vector is. It's one of these arrow type things, magnitude and direction. The head and tail of the vector. So I'll say the head is the section that's pointed, the arrow part, and the tail is where it starts. There's a word that I'm going to try to avoid using, but the UTAs might end up slipping up on occasionally. This word orthogonal. So orthogonal just means at right angles. Orthogonal just means at right angles. So if anytime you hear anyone say orthogonal, you just said at a right angle, it should be pretty much equivalent. So for example, if I say that two vectors are orthogonal to one another, two vectors that are orthogonal are just at 90 degrees. That's all it means. It's just a fancy word for, it makes some things easier to talk about. All right. I already mentioned the word component, but here's what a component is. So if I have my vector, a component is one of the numbers inside the vector. So I might say the second component is v2 here. The third component is v3, and so on. The way that I go from the component representation to the magnitude and direction representation is what I want to talk about here next. Okay, so on the left here, I've got what I'll call the component representation, and on the right, I'll have what I call the graphical representation. So the graphical representation I see has this vector v, it has some length to it, and it lives at some angle relative to, say, the horizontal axis. The component representation is just a collection of numbers, usually just going to be two numbers. So the way that I would convert from knowing, in this case, just the components individually, to over here where I know the length or the magnitude, and the direction or angle. So I'll call the direction this theta, this angle. Theta for angle or direction. The way that I can convert from those two things, between those two things, is actually relatively simple. So I can just do a little bit of not algebra, trigonometry. So just a teeny bit. So this is a right triangle. So if I draw in this little thing here, hopefully that makes it clear. V1 and V2, my x component and my y component here, are the two legs of the triangle, and the hypotenuse is the magnitude. So to find the magnitude of this vector v, the magnitude, so magnitude is these vertical bars, the length of the thing is just the squared sum of the components square rooted. So that's how I get the magnitude of a two-dimensional vector, is I just square the elements and add them together and then square root them. That'll tell me the length of the vector. The way that I can get to this angle measured relative to the x-axis here is by taking the tangent inverse of the two components. So it's going to be v2 over v1. Or in terms of like if these axes are actually x and y, which they typically are, that's going to be tan negative 1 of vy over vx. Okay, and that tells me the value of my angle, theta. So that's how I might convert from magnitude and direction, or sorry, from components to magnitude and direction. If I want to go the opposite direction, let's look at that. So say that I had this vector v, I know its magnitude, I have v magnitude, I have this length here, and I know the angle. So I know the magnitude and the direction. If I want to convert back, now I have to do a little bit more trig. So the x component, I'll call it v1, the x component, vx, is another way to say that. That's just going to be the magnitude v times cosine of the angle, times cosine of the angle. The y component is going to be the magnitude of v times the sine of the angle. All right, so that's my word on magnitude and direction. I'm going to go ahead and box a few things. So this is a good formula to have, good set of formulas to have, as are these. So I'd hang on to these. Cool. If the trig is not familiar, no worries. There will be a short review in DL. And also, I'll try to give a brief one at the end of this if there's time. Okay, see you in the next one.